Welcome! In this session, we'll explore LeetCode problem number 1059, all paths from source lead to destination. This problem challenges us to verify if every path from a source node in a directed graph eventually leads to a specific destination node. It's a fascinating problem that combines graph traversal techniques and theoretical understanding of cycles and connectivity. Let's dive in. In this problem, we are working with a directed graph that consists of n nodes, labeled from 0 to n1. The graph is described using a list of directed edges, where each edge connects two nodes, represented as u, v. Additionally, we are provided with two specific nodes, the source node, where all paths begin, and the destination node, which all valid paths must terminate at. Our goal is to determine if every possible path starting from the source will inevitably lead to the destination. For a path to be valid, it must satisfy two conditions: it must end at the destination node, and it must avoid any cycles along the way. If even a single path either gets stuck in a cycle or fails to terminate at the destination, the answer is false. Otherwise, if all paths meet these criteria, the result is true. Now, let's take a closer look at the input and output formats. The input includes three main components. First, n, which defines the number of nodes in the graph, labeled from 0 to n1. Second, edges, a list of directed edges, where each edge is represented as u, v, indicating a connection from node u to node v. Third, the source node, where all paths start, and the destination node, which represents the target that all paths must lead to. The output of the problem is a Boolean value, true if all paths from the source lead to the destination, and false otherwise. For instance, in example 1, we are given a graph with 4 nodes and edges connecting them as shown. Starting from node 0, all paths lead to node 3, and no cycles are present. Thus, the expected output for this example is true. To elaborate on example 1, the graph consists of two distinct paths from the source node 0 to the destination node 3. One path follows 0-1-3, and the other follows 0-2-3. Since both paths terminate at the destination node 3 and neither encounters a cycle, the result is true. Now consider example 2, where the graph has a different set of edges. Here, there is a path 0-1-2 that does not lead to the destination node 3. Because not all paths from the source end at the destination, the result is false. This highlights the importance of ensuring that every single path from the source conforms to the problem's requirements. In example 3, we encounter a graph with a cycle. The graph includes the edges 0-1, 1-2, and 2-1, forming a cycle between nodes 1 and 2. Starting from the source node 0, any path that enters this cycle will never terminate at the destination node 2. Since paths that enter the cycle fail to meet the condition of ending at the destination, the result is false. This example demonstrates how cycles can prevent paths from reaching the destination, making it impossible for all paths to satisfy the problem's requirements. The presence of cycles is a critical factor to consider when determining the result. Finally, let's examine the constraints and edge cases. The graph can have up to 10-4 nodes and up to 10-4 directed edges, with each edge represented as a pair, u, v. Node indices are always within the range 0 to n1, and the source and destination nodes are distinct. For edge cases, consider a disconnected graph where the source cannot reach the destination. In such scenarios, not all paths lead to the destination. Cycles or self-loops starting from the source also result in false, as they prevent paths from terminating correctly. If the destination node has outgoing edges, it is not a valid terminal node, as paths can continue indefinitely. Lastly, in a single-node graph, the result depends on whether the source and destination are the same. These considerations ensure the solution accounts for all possibilities and edge cases. To tackle the problem of determining if all paths from the source lead to the destination, we need to focus on two critical conditions. First, the destination node must not have any outgoing edges. This ensures it's the endpoint of all valid paths. Second, the graph must not contain any cycles, as cycles would allow paths to loop indefinitely without ever reaching the destination. These two constraints frame the problem and guide our approach. Several strategies were considered to address these requirements effectively, each with its own strengths and weaknesses. The first approach is a brute force method using depth-first search, or DFS. The intuition here is simple: explore every possible path starting from the source node and verify whether all of them eventually terminate at the destination. If we encounter a path that either doesn't reach the destination or enters a cycle, we immediately return false. However, this approach has a significant drawback: it's computationally expensive. Nodes in the graph may be revisited multiple times, especially in cases where paths overlap, leading to redundant calculations. This can result in exponential time complexity in the worst case, making it impractical for large graphs. To address this inefficiency, we move to an optimized DFS approach. By incorporating cycle detection and memoization, we can avoid redundant computations and ensure that cycles and dead ends, nodes that don't lead to the destination, are efficiently handled. Memoization allows us to store and reuse the results of subproblems, while a visited set helps us detect cycles during the traversal. This optimization reduces the time complexity to O, V plus E, where V is the number of nodes and E is the number of edges. Additionally, before initiating the DFS, we perform a quick check to ensure the destination node has no outgoing edges. Lastly, while we also considered using topological sorting, it's not well suited to this problem. Topological sorting works for directed acyclic graphs, or DAGs, but it doesn't directly address cycles or guarantee that all paths lead to a specific node. Topological sorting, while useful for processing nodes in DAG order, has limitations when applied to this problem. Specifically, it doesn't directly address the need to verify that all paths lead to the destination, nor does it handle cycles effectively. The lack of path-specific guarantees makes it unsuitable for our requirements. Considering the problem's constraints and goals, we selected the optimized DFS approach with cycle and dead-end detection. The algorithm begins with a precheck to confirm that the destination node has no outgoing edges. If it does, we can immediately return false. From there, we use a recursive DFS with memoization to explore the graph. If a cycle is detected during the traversal, which occurs when a node is revisited in the current path, we return false. Similarly, if a node leads to a dead end or does not eventually reach the destination, the algorithm signals failure. To avoid redundant computations, we memoize results for each node, allowing us to reuse previously computed outcomes. If every path from the source is confirmed to lead to the destination, we return true. Otherwise, we return false, ensuring a comprehensive and efficient solution. When comparing the different approaches, the brute force method, while conceptually simple, is computationally prohibitive and unsuitable for larger graphs due to its exponential time complexity. On the other hand, the optimized DFS approach efficiently handles cycles, overlapping paths, and redundant computations through memoization, making it the most practical and scalable solution for this problem. Topological sorting, though efficient in DAG scenarios, doesn't meet the path-specific requirements of this problem, making it less applicable. From a complexity standpoint, the optimized DFS approach achieves O, V plus E, time complexity, as each node and edge is processed at most once, and O, V, space complexity to account for the recursion stack and memoization table. This ensures that the solution is not only efficient but also robust enough to handle edge cases like cycles, dead ends, and disconnected graphs. Overall, the optimized DFS approach strikes the right balance between computational feasibility and correctness for this problem. In this problem, we need to determine if every path starting from a given source node in a directed graph ultimately leads to a specific destination node. To solve this, we must ensure three important conditions are satisfied. First, the destination node cannot have any outgoing edges, meaning no further paths should extend from it. Second, the graph cannot contain any cycles, as cycles would create infinite loops and prevent paths from reaching the destination. Finally, for every node that can be reached from the source, there must exist at least one path leading to the destination. To represent the graph efficiently, we use an adjacency list, which is a dictionary where each node maps to a list of nodes it points to. For example, if the edges of our graph are 0, 1, 0, 2, 1, 3, 2, 3, the adjacency list representation would look like this: node 0 points to nodes 1 and 2, nodes 1 and 2 point to node 3, and node 3 points to no one, as it has no outgoing edges. This structure allows us to traverse the graph efficiently during the algorithm. Once we represent the graph, we need to handle some edge cases. If the destination node has any outgoing edges, we can immediately return false because it violates the first condition of the problem. Similarly, if the source node is the same as the destination node, we must check if it has no outgoing edges to determine if this special case still forms a valid graph. To explore the graph, we use depth-first search, or DFS, starting from the source node. During the traversal, we must ensure two critical things: that no cycles are present and that all paths eventually reach the destination. To detect cycles, we maintain two sets: a visited set for nodes we've fully explored, and a visiting set for nodes currently being explored along the current DFS path. If a node is revisited while still in the visiting set, we know a cycle exists, and we can return false. With these mechanisms in place, we can safely traverse the graph while adhering to the problem's constraints. To implement the recursive DFS, we define a function, DFS node, that performs the traversal and checks the conditions. If the current node is the destination, we return true only if it has no outgoing edges. This ensures the termination condition is met. If the node is already in the visiting set, we return false because that indicates a cycle. If the node is in the visited set, we skip further exploration, as it has already been processed. During the DFS, we add the current node to the visiting set to mark it as being explored. Then, for each neighbor of the current node, we recursively call the DFS function. If any neighbor fails to lead to the destination, we return false immediately. Once all neighbors have been explored, we remove the current node from the visiting set and add it to the visited set to mark it as fully processed. Finally, we return true if all paths from the node lead to the destination. At the end of the traversal, we call the DFS function starting from the source node. If it returns true, we can conclude that all paths from the source lead to the destination. Otherwise, we return false. This algorithm has several key insights that make it efficient and reliable. By using the visiting set, we can detect cycles without needing to re-explore the entire graph, ensuring that cycles are identified immediately. Additionally, the algorithm enforces that the destination node must have no outgoing edges, which is a strict requirement of the problem. To improve efficiency, we avoid redundant exploration using the visited set, which tracks nodes that have already been fully processed. By handling edge cases like checking for outgoing edges at the destination upfront, we further reduce unnecessary computation. For the complexity analysis, the time complexity is O, V plus E, where V is the number of nodes and E is the number of edges. This is because each node and edge is visited at most once during the DFS. The space complexity is O, V, due to the recursion stack and the use of the visited and visiting sets. With this foundation, we can now look at the Python implementation of the algorithm. The Python implementation starts by constructing the graph as an adjacency list using the defaultic from the collections module. Each edge is added to the graph representation, mapping a node to its neighbors. We first check if the destination node has outgoing edges, and if it does, we return false immediately. Next, we initialize the visited and visiting sets to track the nodes during traversal. The DFS function is then defined. If the current node matches the destination, we check if it has no outgoing edges. If the node is in the visiting set, a cycle is detected, and we return false. If the node is in the visited set, we return true, as it has already been processed. For nodes that haven't been visited, we add them to the visiting set and recursively call DFS for each neighbor. If any neighbor fails to lead to the destination, we return false. After exploring all neighbors, the node is moved from visiting to visited, marking it as fully processed. Finally, the DFS function is called from the source node, and its result determines the output of the algorithm. To understand the algorithm in action, let's go through an example. Suppose we have 4 nodes, edges defined as 0, 1, 0, 2, 1, 3, 2, 3, the source node is 0, and the destination node is 3. First, we build the adjacency list, which results in the graph. Node 0 points to nodes 1 and 2, nodes 1 and 2 point to node 3, and node 3 has no outgoing edges. We check if the destination, node 3, has outgoing edges. It does not, so we proceed. Starting the DFS from node 0, we explore its neighbors. Visiting node 1, we proceed to its neighbor, node 3, which is the destination and valid. Backtracking, we explore node 2, which also leads to node 3. Since all paths from node 0 lead to the destination, the algorithm concludes by returning true. Here, we begin by importing the necessary modules and setting up the solution class. To represent the graph, we use a default dict where each key maps to a list of its neighbors. This makes it easy to store and retrieve adjacent nodes for any given node. We then iterate through the edges list, adding each directed edge to our adjacency list. Next, we handle a critical edge case. If the destination node has any outgoing edges, it's impossible for all paths to terminate at the destination, so we immediately return false. After that, we define an array, state, to keep track of the visitation status of each node. Each node can be in one of three states: 0 for unvisited, 1 for currently being visited, and 2 for fully processed. Now, we define a depth-first search function, DFS, to explore the graph recursively. If we encounter a node that is already being visited, this indicates a cycle, meaning not all paths lead to the destination, so we return false. If the node has already been fully processed, we skip further exploration and return true. Finally, before exploring its neighbors, we mark the current node as visiting by setting its state to 1. The next step in the DFS function is to check if the current node has any outgoing edges. If it doesn't, the only way it can satisfy the problem's conditions is if it directly matches the destination node. If it's not the destination, we return false since the path doesn't terminate correctly. Otherwise, we proceed to recursively explore all the neighbors of the current node. If any neighbor fails the DFS check, we immediately return false because this means not all paths lead to the destination. Once all neighbors are successfully explored, we mark the current node as fully processed by setting its state to 2. This helps optimize future calls to DFS by avoiding redundant calculations for nodes we've already verified. Finally, the function returns true, indicating that the current path segment satisfies the problem's conditions. At the end of the implementation, we initiate the depth-first search by calling DFS with the source node and return its result. Here, we start by importing the necessary classes and defining our solution class. The main method, leads-to-destination, takes 4 parameters: the number of nodes in the graph, the list of edges, the source node, and the destination node. The first step is to construct an adjacency list representation of the graph using a hash map. This allows us to easily look up the neighbors for each node. For each edge, we add the destination node to the list of neighbors for the source node. Next, we include a critical check. If the destination node has any outgoing edges, the function immediately returns false. This is because the problem requires all paths to terminate at the destination, and outgoing edges would imply the destination is not a dead end. Finally, we initialize an array called state to keep track of the visitation status of each node during our depth-first search. The states are represented as integers: 0 for unvisited, 1 for visiting, and 2 for fully processed. The DFS helper function is then called to start the depth-first search from the source node, and its result determines the return value of the method. The DFS method implements the core logic for checking if all paths lead to the destination. First, if the current node is marked as visiting, state 1, this indicates a cycle, and we return false since cycles prevent paths from terminating. If the node is already fully processed, state 2, we return true because we've already confirmed that all its paths lead to the destination. Next, we mark the current node as visiting by setting its state to 1. We then check if the node has no outgoing edges. If it doesn't, we check if it's the destination. If it is, we return true because we've successfully reached the end. Otherwise, we return false since a non-destination node with no outgoing edges violates the problem's requirements. Now, we recursively explore all neighbors of the current node. If any neighbor fails the check, we immediately return false. Finally, if all neighbors pass the check, we mark the current node as fully processed by setting its state to 2 and return true to indicate that all paths from this node lead to the destination. The implementation concludes here with the closing braces for the DFS method and the solution class. At this point, the code is complete and fully functional. The leads-to-destination method, combined with the recursive DFS helper, ensures that all paths from the source node are validated to either terminate at the destination or fail if any path violates the problem's constraints. This approach leverages depth-first search for graph traversal, along with cycle detection and state management, to solve the problem efficiently. To solve this problem, we start with a simple example where the graph consists of 4 nodes and edges that form a straight path from the source, node 0, to the destination, node 3. First, we construct the graph using the given edges. This results in an adjacency list where each node points to its neighbors. Node 0 points to node 1 points to node 2, and node 2 points to node 3. Notice that the destination node, 3, has no outgoing edges, which is a key requirement. Next, we initialize a state array to keep track of our progress through the graph. All nodes are initially unvisited, so the state array is 0, 0, 0, 0. Now, we perform a depth-first search, DFS, starting from the source node, 0. We mark node 0 as visiting by updating its state to 1, and then proceed to explore its neighbor, node 1. From node 0, we move to its neighbor, node 1. We mark node 1 as visiting by updating its state to 1. Then, we continue the DFS by exploring node 1's neighbor, node 2. At node 2, we mark it as visiting and proceed to its neighbor, node 3. When we reach node 3, we mark it as visiting and check if it's the destination. Since it is and it has no outgoing edges, we can return true for this DFS path. Now, we backtrack through the graph, marking nodes as fully processed. Node 3 is marked as fully processed with a state of 2, then node 2, node 1, and finally node 0 are also marked as fully processed. The final state array becomes 2, 2, 2, 2, indicating all nodes have been successfully processed. Since every path we explored leads to the destination, the output for this example is true. Now, let's look at a graph with a cycle. This graph has 3 nodes connected such that node 0 points to node 1 points to node 2, and node 2 points back to node 0, forming a cycle. The source is node 0, and the destination is node 2. When we construct the adjacency list, we see that while nodes 0 and 1 each have outgoing edges, node 2, which is the destination, also has outgoing edges. This violates one of the core requirements of the problem, which is that the destination must not have any outgoing edges. Therefore, we can immediately conclude that not all paths can lead to the destination, and we return false as the output for this example. In this next example, we have a graph with dead ends. The graph consists of 4 nodes. Node 0 points to both node 1 and node 3, and node 1 points to node 2. The source is node 0, and the destination is node 2. First, we build the adjacency list, which shows that node 0 has 2 neighbors, nodes 1 and 3, and node 1 points to node 2. Node 2, the destination, has no outgoing edges, which satisfies one of the key requirements. We initialize the state array as 0, 0, 0, 0, and start a DFS from the source, node 0. We mark node 0 as visiting and explore one of its neighbors, node 1. From node 0, we visit node 1, marking it as visiting. Then, we proceed to explore node 1's neighbor, node 2. At node 2, we mark it as visiting and confirm that it is the destination with no outgoing edges. This path is valid, so we return true for this branch. We then backtrack, marking node 2 and node 1 as fully processed. Returning to node 0, we explore its other neighbor, node 3. We visit node 3, marking it as visiting, but find that it has no outgoing edges and is not the destination. This means the path to node 3 is invalid, so we return false for this branch. Since not all paths from the source lead to the destination, the output for this example is false. The time complexity of our solution is driven primarily by the depth-first search, or DFS, traversal of the graph. First, we need to build the graph using an adjacency list. This involves iterating over all the edges, so if there are e edges, this step takes time. Next, during the DFS traversal, we visit all the nodes in the graph. For each node, we process all its outgoing edges, meaning that every edge is processed exactly once. This traversal results in a time complexity of n plus e, where n is the number of nodes and e is the number of edges. Additionally, there are some minor operations like checking if the destination node has outgoing edges or marking nodes as visited. These operations are constant time, 1, for each node. Altogether, the graph construction and traversal dominate the time complexity, making it n plus e. Thus, the overall time complexity of our solution is n plus e, as it accounts for both constructing the graph and performing the DFS traversal. Now, let's discuss space complexity. The space complexity depends on the memory used for the adjacency list, the state array, and the recursion stack. The adjacency list, which represents the graph, requires n plus e space because it stores n nodes and e edges. To track the visiting or visited state of each node, we maintain a state array of size n, which adds an O(n) space requirement. Finally, the DFS recursion stack grows with the depth of the graph. In the worst-case scenario, such as a graph that forms a long chain, the recursion depth can reach O(n). In a more balanced graph, the depth would depend on the longest path. Combining these factors, the dominant term for space complexity is O(n plus e). Taking everything into account, the total space complexity is O(n plus e), which includes the adjacency list, the state array, and the recursion stack. Now, let's analyze the algorithm under different scenarios. In the best case, the graph is sparse, meaning it has relatively few edges, and the DFS traversal terminates early due to detecting a cycle or reaching a dead end. Even in this scenario, the time complexity remains O(n plus e), but the constants involved are smaller. In the average case, the algorithm explores a reasonable portion of the graph, and the time complexity remains O(n plus e). In the worst case, the graph is dense, meaning it has many edges, and the algorithm must traverse every node and edge. The recursion stack may also reach its maximum depth. Despite this, both time and space complexity remain O(n plus e), as the algorithm efficiently processes each node and edge exactly once. When comparing approaches, a naive solution might attempt to generate all possible paths from the source and check if they lead to the destination. However, this results in exponential time complexity, O(2 to the power of n), due to the sheer number of paths in the graph. In contrast, the optimized approach leverages DFS with cycle detection to avoid enumerating all paths. By marking nodes as visiting or fully processed, it efficiently handles cycles and prevents redundant work. This reduces the time complexity to O(n plus e). Mathematically, the optimized solution visits each node once and processes each edge exactly once, ensuring that the time complexity is O(n plus e). The adjacency list representation also keeps space usage linear, resulting in O(n plus e) space complexity. Overall, this approach is efficient for both sparse and dense graphs, offering optimal performance within the problem's constraints. When working on this problem, there are some common pitfalls to watch out for. First, many solutions incorrectly assume the graph is a tree, meaning acyclic and connected, but the problem allows for cycles and disconnected components. This assumption is dangerous because cycles can make a path infinite, and disconnected nodes might lead to paths that never reach the destination. Another frequent mistake is not properly handling cycles in the graph. If cycles aren't detected and handled, the algorithm might loop infinitely or falsely conclude that a path is valid. Lastly, failing to check if the destination node is a terminal node, that is, ensuring the destination has no outgoing edges, can lead to errors. If the destination has outgoing edges, it's impossible for all paths to terminate there, which directly violates the problem's requirements. Additionally, mishandling disconnected graphs is another mistake to avoid. Some solutions ignore the possibility of nodes being unreachable from the source or fail to explore all valid paths from the source. This can result in overlooking key scenarios and producing incorrect results. Another challenge is inefficiency. Using brute force without optimization, such as memoization or visited node tracking, can lead to a time limit exceeded error. This happens because the algorithm ends up revisiting the same nodes multiple times, especially in graphs with cycles or a high branching factor, causing exponential time complexity. Being mindful of these inefficiencies is crucial for solving the problem within the constraints. This problem is a great opportunity to demonstrate key insights during an interview. At its core, it combines graph traversal techniques like DFS or BFS with cycle detection. Being able to handle edge cases such as cycles, disconnected graphs, and invalid terminal nodes will reflect your ability to solve complex graph problems. It's also important to highlight the patterns you notice, like how cycles and terminal conditions impact the structure of a graph. This is highly relevant to real-world scenarios, such as resolving dependencies in package managers. Be prepared to explain trade-offs between DFS and BFS approaches, including when memoization is necessary for optimization. Mentioning specific edge cases, such as graphs where the source has no outgoing edges or graphs with cycles that don't involve the destination, shows thoroughness. Finally, you can connect this problem to related ones, like course schedule or eventual safe states, which share similar concepts like cycle detection and terminal node identification. Now let's consider some alternative approaches and their trade-offs. One approach is using DFS with cycle detection. This involves recursively traversing the graph and keeping track of visited nodes to identify cycles. While this method is simple and intuitive, it can become inefficient without memoization, especially in larger graphs. Another option is topological sort, which uses topological ordering to determine if all paths lead to the destination. This approach works well for directed acyclic graphs but isn't suitable for graphs with cycles. Finally, reverse graph traversal is an interesting alternative. By reversing the graph and starting the traversal from the destination, you can ensure all nodes in the reversed graph are reachable from the source. While this method can simplify backtracking in some cases, it requires pre-processing to reverse the graph, which adds an extra step to your solution. Understanding these approaches and when to use them will help you choose the most effective solution for this problem. Great job! To recap, we used depth-first search to determine if all paths from the source lead to the destination. This involved checking both cycles and terminal conditions in the graph. Remember, mastering problems like these strengthens your understanding of graph theory and traversal algorithms. Thanks for tuning in, and don't forget to like and subscribe for more problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!